All right, good morning, everybody.
Morning.
Morning.
So, first thing I want to talk about today is recording lectures. And so I posted an announcement about this yesterday, and I do this with a fair amount of hesitation, but for this week at least, I'm going to record our Zoom lectures and post them on YouTube. With a lot of disclaimers and caveats and details around that that I want to talk about right now. So the first and most important thing is I want to absolutely respect student privacy, which means, number one, if for any reason you're uncomfortable with my recording and posting recordings of these lectures, let me know. You can let me know right now. You can send a private chat message if you want to, just talk to me one-on-one, or, anytime down the road, you can send me an email message and say, I'm not comfortable with this, and that will be enough for me to stop doing this. All right. So I don't want anybody to feel, peer pressured. I will not, disclose if someone sends me a message and says, I really am not comfortable with this, and I decide to stop recording. I'm not going to say, so-and-so wasn't happy with this, and so you can blame them, right? This is something I can only do if everybody is in agreement with my doing it. And so if there's ever a concern, just let me know, and that's all it will take. Secondly, during class, if, for example, you want to ask a question on microphone and you don't want your voice recorded, send me a message in chat. And again, you can send me a private message if you want, and just say, hey, can you pause the recording? And I can hit a button that will pause it. I tested this out yesterday and it works fine. And then when you're done, say, okay, you can record and I'll resume it. And so there may be gaps in there where students ask questions and so on. So that's the second thing. And I'll keep this little tag up here in the corner saying recording in progress, just to let people know this is going on. I don't know if Zoom is giving you its own indication that I've got recording on, because I'm doing this recording through Zoom. And so it may be giving you this information also. It does. Cool. Awesome.
Can I ask a question?
Go for it.
So I going to post the course video on the canvas or no?
So I will put it in a playlist on YouTube, and I put a link to that playlist in Canvas. And until I get this first video uploaded, I can't guarantee that that's the correct playlist link, but it should be. And I'll upload it right after class, and then you should be able to get to it.
Thank you.
Yeah, you're welcome. So the third disclaimer is that, in the past, I've done some post-production on videos. I've added tags to them. I've timestamped the tags and made it so that those tags are searchable, and so on and so forth. I'm not doing any of that this time. I'm just posting the raw video. The only editing will be if I pause it during lecture. And so it's kind of a, here it is sort of situation. And that ties into my fourth caveat, which is please do not stop coming to class just because I'm posting videos. The videos are not a stand-in for coming to class and participating. The videos are there because, every week I have students who are on travel, who are having, some kind of emergency where they have to be somewhere else other than class, or their work schedule got changed and they have to be at work during class time. Right, most of us have fairly complex lives, and so these situations keep occurring, and the videos can be a nice sort of last opportunity to catch some of what's going on in class, rather than just, missing a class or a week and having no idea, and then having to, scramble to try to catch up. But statistically, based on when I've done recordings in the past, if you do not come to class regularly, you have at least a 50% chance of failing. Either failing the course or deciding that you don't have enough understanding to continue with the sequence. But historically, 50% of the students don't make it through the sequence, at least 50%, if they stop coming to class. That's not a policy, it's just a statistical observation. So please, keep doing what you're doing, come to class, make the effort, be here on time, pay attention, take notes, participate. And if something's not making sense, don't just think, okay, I'll go back and watch the video later and try to catch this again. Stop me while I'm talking and say, hey, can you re-explain this? Can you answer this? Can you go over that again? And so on, right? I want you to still think of this as a face-to-face class that has Zoom in between our faces, basically. So use the videos if, something unexpected, unavoidable happens, and your alternative is I completely missed the lecture, right? Then go ahead and use the videos. But other than that, I'm going to ask you to kind of, keep it as if there were no videos available, basically. So that's my set of disclaimers. Our attendance has dropped already. Last week we were missing about 20% of the class each week. But in the past, when I've done this, attendance drops down to where, like, maybe 1 in 4 people are coming. And if that happens, I will probably stop recording, just because that's a really bad situation. All right, so my goals for today are to talk about ODP 414 from last week, because we ran out of time for that. That was the mix function. So I want to take a quick look at that. I want to look at the new ODPs, which posted for yesterday and today. So 416 and 417, which opens tomorrow. And then mostly I want to spend today talking about PA2 and working through pseudocode for the different functions that we're going to implement, and thinking about how we can actually write some code for those different pieces of the index program. Oh, the other thing I want to do before PA2 is go back and make one more comment on make files that we didn't get to on Thursday, which is this make clean option, which is part of the make file requirements for PA2. So that's the basic agenda. And then if we get through all of that, I want to start talking about GDB. That's our debugger, and how we can use this tool to help us find problems with in particular C programs. So any questions or things that you want to talk about before we start all of that?
I have a question.
Okay.
And it kind of comes back to your main program,
Mhm.
PA2. Sorry, I think I've been overthinking this part a little bit, because I'm kind of worried that I'm going to use something that maybe you don't like include in your main. I suppose it would be in my header file, but do you plan on just having your main essentially just call the functions?
Basically, yeah.
Yeah, okay, cool. Awesome, thank you.
Yeah, you're welcome. And we'll pseudocode main also, and we'll see that it's a really short main function that really just kind of leans on these other functions that you're developing. All right, so let me go ahead and look at the ODPs first. There we go. So 414, which was last week, but we didn't get to talking about it. This was this mix function that takes 2 strings of equal length and interleaves them like this. to create a new output string called out that is a combination of the letters from each. And we talked through, you know, the basic idea of this, but we didn't really get into details. So let me show you a function that can do this. And the main idea here is this idea of building an output string. So this function takes two inputs, S1 and S2. These are sent to you by, you know, whoever is calling you. You're going to call this, you're going to pass a string A and you're going to pass a string B. And the mix function creates this new string out and sends that back. So how do we build a string? Well, in this case, we're building it character by character. We're just taking the first character of our first string, that's S1 bracket 0, and we're putting that directly into our output array. And so if in is like, you know, ABC, or let's call this S1 is ABC and S2 is 1, 2, 3. Our goal is to make an output string, which is first character of S1, first character of S2, second character of S1, second character of S2, third character of S1, third character of S2. And one way to do that is to, you know, we can read these characters inside a for loop. So we can make a for loop that runs from 0 to the length of our strings. S1 and S2 have the same length. So from 0 to, you know, less than string length of S1. So in location, the first time through the loop will be 0, which gets these characters, and then 1, which gets B and 2, and then 2, which gets C and 3. And inside our loop, what we need to do is take these and build an output string. And if we think of this now as an array of characters, here's where we want to store the characters from S1 and S2. The character from S1 goes at location 0. The character from S2 goes at location 1. The second time through the loop, when we read the B, that goes at location 2. And the next character from S2 goes at location 3, and so on. Now we could do some sort of fancy calculations based on where we are in the string to know where we should store the next character in our output string, but we don't need to be too fancy. What we're going to do is we're going to have some output location index that we initialize to 0. And each time we want to store something in our output string, we're going to put it in out bracket output location. And then we're going to increment output location like that. So out location starts at 0. This for loop is iterating through the input words, right? So for the first value, first time through this loop, in loc is 0. This is the first character of the first word. This is the first character of the second word. So to copy this to our output, we just copy it into out bracket outloc. And I'm doing a plus plus at the end here. That's doing the same thing as outloc equals outloc plus 1. So I mean, I could do it like this. All right, so copy our first character into our output array and increment the index so that the next time we do the same statement, our character gets stored at the next location in our output array. And this sets it up so the next time we execute this statement up here, character gets stored at the next location in our output array. So outloc is this is the index where we want to store the next character in out. I don't know what I did there. Does that make sense?
Yeah, so basically you have your strings coming in. I see. So you're always incrementing it after you set one of the strings equal to that index, and then it increments, and I'll do the next one. Okay. Yeah, that makes sense.
Exactly.
Hmm.
And this is a really powerful technique. This is going to work for the other ODPs that we're doing this week, 416 and 417, I think they are. And this is going to work for part of PA2 when you try to build a word. Same idea. The basic setup is we're getting stuff one character at a time, and we want to be building some kind of string out of those characters. And this sort of thing will work really well for that.
So I actually have a question.
Yeah.
Because I kind of did this two ways. One the way you did, and then, I saw a lot of people talking about string copy. So I use string copy. Are they essentially the same thing, or is there something with string copy that we might like watch out for?
So the issue with string copy is it only works on strings, meaning things that are terminated by nulls. And while we're building this output array, it's not legally a string. Now we may luck out and it may have a bunch of nulls to begin with, but it may not. And if we try to string copy, or string append to out with string cat or something like that, we may get gibberish, we may seg fault. And so if you can do it, sort of at this low level, you're guaranteed it's going to work. But we will talk about string copy with respect to PA2. That's going to be a useful function for like read keywords, for example. We're going to want to use string copy, but we wouldn't have to. We could also do a string copy with just a for loop, right? And loop through your whole string and assign output characters based on the input characters. But yeah, I think string copy is hard to use for this because we've got two strings and they need to get mixed together.
Yeah, I'd actually be interested in that because I know on my read keywords, I could only figure out how to make it convert to uppercase, like with the for loop.
Okay, yeah. So
I
for
couldn't get
the
string copy
uppercase,
for
you need to use a for loop.
Yeah, cool. Awesome.
Because two upper works on characters.
Thank you.
Yeah. So there's this last business here of terminating the string. And the deal here is, if we copy these 6 characters into out, right, we don't necessarily know what's in index 6, the 7th character. If it happens to be a null terminator, everything is great. But it may turn out to be, some stray character. And in fact, there could be, 1,000 stray characters sitting here in memory. And until we find a null terminator somewhere, our string could have a whole bunch of other stuff in it. So when we're done copying these 6 characters into here, we really want to throw a null terminator right there. And again, how do we know where to put it? Well, we could do some calculations, but we have this notion that outloc is always where we should store the next character. And so when it's time to put on the null terminator, where do we put it? We can just put it at outloc. And that's going to go right at the end of the characters that we've meant to put in the string, and we'll get a nice, well-behaved string. So yeah, good comment in chat. Someone said, with pointers like strings, C will drive a car off a cliff before checking with you to make sure it's all right. Absolutely. That's a good way to characterize it. C will do pretty much whatever you want. And if it makes no sense, it'll still do it. C is very much like assembly language. It's a higher level version of assembly language, but it's really kind of operating in a lot of ways at the same level as assembly language. And, assembly language, if you've done engineering 270, you can tell it to do anything you want, and it doesn't have to make any kind of sense. It'll just happily do it because it's just, a bunch of instructions it's following. So C is very much like that. And welcome back. All right, so this was ODP 414. We'll play around with this code again when we play with a debugger. But let's look at 416. So this ODP is live right now. And for this assignment, your goal is to write a function called remove. And remove takes two arguments, an input string and an output string. And the idea is it should take this input string, remove all the lowercase x's from it, and put the result in this output string. So if we say remove hexaflexagon, comma, out, what should happen in here is out should be changed into HE, no X, AFLE, no X, agon. So he a fleagon. And if we think about this idea from ODP 414 of building an output string, this is pretty straightforward. So for each, so let's call this, you know, remove in, comma, out. So for each character in, if it's not equal to an X, add that to our output string. Oh, sorry to hear that. Hope that's okay. All right, so this is our main loop. And then when we're done, we have to do something to terminate our output array, just like in 414. So it's in some ways a simpler program than 414, right? We're just looping across one input string, grab each character, right? So you know, get a hold of each character inside a loop by doing something like that. And only assign it to your output string if it's not equal to an X. So some kind of if statement, you know, C equals input bracket in location. If C is not equal to X, then out bracket out location equals C. And only increment that output location if you assign something to it. And at the end, do something to throw a null terminator on the end. So your remove function is prototyped like this: two car pointers, an input and an output. You're allowed to use the string length function, right, which is useful for iterating through your input string. But all your other code should just be code that you write using basic C. And you're going to want to write a main program to test this. So your main program could be something like, you know, character out bracket 120, and then call your remove function, and then do a printf out equals %s. Right, and that's a nice piece of test code for driving this. So make an output array, call the remove function, which should remove the x's from here, store the result in out, and then just use a print statement to print out, and see if it's, you know, he a fleagon. And try this with different strings. Try with an empty string, try with a string that contains only x's, try with a string that contains an x in the beginning, try with a string that contains an x at the end, try with a string that contains x's in the beginning, middle, and end. And once you're pretty sure that it works, then you can go ahead and assess it. So if your function is in a file called remove.c, you can build a test program by using this compile statement and then assess it using this. All right, any questions on 416? And then 417, which opens tomorrow, is almost exactly the same with one subtle change. The one subtle change is this remove one function only removes the first occurrence of the letter X. So if I called remove one with hexaflexagon, the output would be HE, that first X would get removed, but this would still be flexagon. So the second, third, fourth, all the subsequent X's still appear. And that only takes a little bit of extra code to manage. And really all you need to do is use a flag. So you could create a variable like we could make a variable called skipX and initialize it to 1. And inside here, if the character is not equal to an X, we want to add it to out. If it's equal to X and skipX equals 0, we want to add it to out. But if it's equal to X and we're saying we should skip X's, change our skip X to 0, but don't add it to out. So we're using a flag. And in this case, I'm initializing the flag to 1. And if this is 1, it means don't add an X to the output. And the first time I find an X, if that flag is set, I'm going to clear that flag. I'm going to skip that X, but since I clear that flag, the next time I find an X, it'll say, oh, I'm not skipping X's anymore. It'll go ahead and add it to the output. Or, you know, I could make a flag called I've already seen an X and initialize that to 0. And then when I see an X, I can set that to 1. And when I encounter an X, if I've not already seen a 0, I'll skip it. Otherwise, I'll add it. And this is an example of what I sometimes call stateful programming, right? So it's looking at a set of code that does different things depending on what's happened in the past. And so in this case, you know, if I've never seen an X, my code will skip it. If I have seen an X, my code will take an X and just add it to the output like any other character. So the same set of code does two different things. Some of you use this idea in your stick program for PA1. We're going through the code of your main loop. Sometimes it would ask the user how many sticks. Sometimes it would decide how many sticks it was going to take. Same set of code, but the behavior depends on what state the system is in, what's happened in the past. So this is another powerful idea that comes up a lot in programming.
So just so I'm clear on this second one we're talking about with the flag, like if we were to put this into your hexaflexagon thing, it would just turn it into heaflexagon. It would keep the second X. Is that right?
Exactly.
Oh, okay, cool. Thank
And
you.
if there were other X's, it would keep those as well. So this is a good time to mention that there's an additional textbook that you can download from Canvas called I Can See Clearly Now. This is a book that I wrote specifically for this course in CSE224. And it's meant to kind of like, you know, bridge whatever gap there might be between Knowing, how to write C programs, knowing the syntax of C and such, bridging from there to being able to do more powerful things in C. And so one of those things is state-based programming, right? And there's 5 pages in here that talk about state-based programming. Another part of that is string processing. So this idea of building an output string 1 character at a time, iterating over a string, using a for loop and so on and so forth. That's chapter 3. And these are not long chapters. They're several pages at the most, right? But a lot of what we're talking about, you can find in here. You can find other examples. You can find exercises to work on and so on and so forth. This first real chapter 2, is talking about all the stuff we used in PA1. The idea of using fgets and scanf together. The idea that we don't really want to use scanf because it can throw our program into infinite loops sometimes and so on. There's a homework assignment due tomorrow. Don't forget to do homework 3. It's been on Canvas since before the quarter started, and it's a Canvas quiz. And so it's got a little bit of code. You type it in, you run it, and you answer questions about it. So hopefully people have done that, but if you haven't, I think it's due tomorrow morning at 8. So make sure you do homework 3. And it's a hands-on lab exercise basically that deals with, this business from PA1 of scanf and scanf and fgets. In CSE224, we'll deal a lot with pointers, and this may be helpful to you. But this also talks about argc and argv, possibly in more detail than you need for CSE224, but definitely for 222, you'll want to understand it. So this is a good chapter to think about. And recursion will pop up a lot in 222. That's the main thrust of it. We started talking about makefiles last time. Here's a chapter on makefiles. So this is a useful PDF to download, and you can link to it through Canvas and pull it down. And none of it is very long or particularly wordy. It's really just kind of pretty bare bones presentation of some of these ideas. So that's something I wanted to mention again.
So is that just free? And are you all right if I just download that onto my computer? Or
you can download it, you can put it on websites, you can sell it if you can get anybody to pay money for it. It's totally open source, so you can do whatever you like with it. It's on Amazon only because I wanted to be able to get hard copies, and that's a really cheap way for me to get hard copies of books, is to make them available on Amazon and then buy them. But yeah, it's a free PDF download. You can do anything you want with it.
okay, cool, thanks.
Yeah, you're welcome. All right. Questions on the ODPs? All right, so we were playing with makefiles on Thursday, and we had this makefile set up that would let us say make, and it would try to find these object files, and if it found them and any of them was newer than our executable, it would go ahead and relink those to build our executable program. And for any of these, like fun.o, it would look at how fun.o is created. It depends on fun.c and main.h. And if either of these files was newer than the object, it would rebuild the object. And once it did that, fun.o would be newer than main, and so it would rebuild main. And so we put together this make file with the idea that we could say make, and if everything was up to date, it would just tell us everything's up to date. But if we edited a file like coolfun.c, and then we say make, it will realize, oh, coolfun.c is newer than the object. It'll recompile that. And then it'll say coolfun.o is newer than main. And so it will relink all of the objects to create a new main program. And then if I say make again, it'll say everything's up to date. And if I have a header file like main.h, and you need a header file index.h for PA2, I can specify on here, for example, that to build my object main.o, I need to use not only main.c, but main.h, because main.c includes main.h. So in my make file, I actually have two files that depend on main.h. And so if I touch that, and touch file name just changes the access date on it. So if I touch that and I say make, it recompiles main.c. Why? Because I said main.o depends on main.c and main.h. Since this file is newer than the object, it's going to rebuild main.o. And then same thing down here. I said that fun.o depends on fun.c and the header file. Since the header file is newer than the object, it rebuilds the header file, the object, by saying compile fun.c. And now main.o and fun.o are newer than main, and so it rebuilt the executable. And now main is up to date, and if I say make again, it tells me it's up to date. So the idea of all of that was that, as you're working on a project like PA2, which has, at least 6 separate files, when you make changes to a file, instead of having to go back and, recall the GCC command and so on and so forth, you just say make. And it will recompile whatever needs to be recompiled. It will relink what needs to be relinked and leave you with an executable program. And so your development process gets more streamlined, right? VI code, make, and then run your program. And if there's a problem, VI your code, make your changes, say make, run your program.
Do you need to include the .h files in the GCC commands?
Well, no. So here's my fun.c. And I can just say gcc-c fun.c, and that'll compile it. Just like when we have a main program and we say include stdio.h, we can compile this by saying gcc main.c. We don't say main.c standard.io.h, right? We just say main.c, and the compiler, when it looks in main.c, will say, oh, I need to include the contents of this file, and it'll pull that file in.
That makes sense.
So we really don't want to include it. And if we did include it, we get funny business going on where we've got this main.h.gc file kicking around in here. And that's not something we want to do. Right? We can look in here, really, there should not be any code in here that produces anything that, has assembly language to it. This is information for the compiler. This is information. When we have defined statements, that's information for the compiler. So this is not stuff that has to get compiled. It's stuff the compiler needs to know in order to compile, say, fun.c. So I'm revisiting make files because there's one other thing that PA2 asks you for that we haven't talked about, and that's this idea of a clean target. And the idea of a clean target is, I've got my code here. Maybe I push all of this into Git, right? And I download your code from Git, and here's what my repository looks like. And the first thing I want to do is see, does your code compile? And so I'm going to say make, and it's going to say main is up to date. And the only way I can get it to recompile coolfun.c is if I delete coolfun.o or I touch coolfun.c. And to get it to compile fun.c, I have to delete fun.o, or I have to touch fun.c, and so on. And this is a pain. This is a lot of work. This is not stuff that I necessarily want to have to do. And so most make files include what we call a clean target. And it looks something like this. I'm going to make a target named clean. It's not going to have any dependencies, and my recipe is going to say remove pool fun.o, main.o, and main. All right, so what does this do? If I say make, it says main's up to date. If I say make clean, it removes those objects that were compiled. It removes the executable program. And now when I say make, it recompiles everything. So if for some reason you want to force everything to be recompiled, all I have to do is say make clean and then make. And one of the main reasons for this is, you know, again, think about Git. Suppose I finish my project and I push all of this to Git and I tell the world, hey, you know, I've got a really cool program. It's cool and it's fun. Here's the GitLab repo, and people download it. And the issue is, you know, this main program, this runs on an x86 machine. That's what I compiled it on, was my laptop. And so it runs on a laptop just fine. But maybe the person who's using this is using something like this. This is called a Corral Dev Board. It's a machine learning processor from Google, and it runs Linux. And if I'm connected to this machine and I download this repository and I try to run the main program, it's not going to run, because this is not an x86 based machine. This is using an architecture called ARM. And so I download the code and I try to run it, and it's going to say invalid executable. And in order to make it runnable, I have to recompile it. Well, if I say make, it's going to say main is up to date. It's not going to recompile everything. And now I have to go in and I have to start compiling things by hand or deleting files and hope I don't delete the wrong thing, and so on and so forth. But if the person who made the make file gave me a clean option, I just say make clean, right? And I do this on my new machine. And now when I say make, the GCC that runs on my new machine will compile code in the language that my machine understands. And this will leave me a different executable main that actually runs on the hardware that I'm sitting on. And so as people move away from x86 and you know, to ARM processors and things like that, this becomes an increasingly common use case. All right, so you definitely want a clean option, and it's a bit of a trick, right? This is a recipe that builds a main program. This is a recipe that builds an object. This builds an object. This builds an object. This doesn't build anything. It gets rid of stuff actually, but make doesn't care. Make simply says, hey, if you say make clean, look for a target named clean. Make sure these dependencies are satisfied. Well, there's no dependencies, so that's fine. And then execute this command. So a student in the other section came up with the idea of making another target called save, I think. And if she says make save, the command for that is the git commands, git add, git commit, git push. And so as she's working on her project, she can build a new version of it by saying make, but she can also say make save, and it pushes everything over to GitLab for her. And this is, you know, this general spirit of we want to concentrate on writing code, coming up with algorithms, debugging code, right? These are the things that we are going to be really good at. We don't want to spend our time typing, you know, or going back and recalling commands or going back and editing commands and so on. That's not our deal, right? We're programmers, we're coders, we're debuggers, right? That's where we want to spend all of our energy and attention. And compiling a program, I don't want to type GCC. I don't want to go back and think about it. I just want to say make, right? And so this streamlines our production. It lets us keep our mindset on what we're trying to do, which is, develop algorithms, implement them in code, debug them, test them. So make files are just a win across the board. The only downside is, you have to make a make file. And it's a little bit like the leaky roof problem, right? If you have a leaky roof, you don't want to fix it while it's raining. And if it's not raining, it's not a problem, so you don't fix it. But, you end up with like water all over the place. So make files are kind of the same way. If your program is really simple, you don't want to write a make file just to compile one program, right? But if your program is very complex and you have 20 different files, it's really hard to make a make file. So it's one of these things you just got to kind of do up front and keep it updated. If you add a new file to your project, update your make file, right? But it will pay off in the end for the convenience of just being able to say make. Or, if everything gets haywire, just being able to say make clean and then say make and rebuild everything. All right, so that's the whole spiel on make files. And there's a video link on Canvas under that possibly useful videos. There should be a link there to make files that basically goes over everything we've talked about, including this make clean option. So you can look at that for revisiting some of this, or ask questions. All right, so questions on any of that? All right, so we are ready to talk PA2 details. Let's number of times I've deleted gigabytes of Gradle cache just to re-download. Yeah, right. So yeah, make files, there's lots of different versions of make. And so Gradle is another way of defining the parts of a project and controlling what gets compiled and linked and so on and so forth. And these things, on large projects, on Android Studio apps and so on, these get really big and really complex. And a lot of times we're not actually going in and making a make file. We have an IDE like Android Studio that's creating these things for us and using them. But it's still, something like a make file under the hood. And they can get pretty complex and funky. All right, well, let's take our break right now. And let's come back in about 5 minutes, and then we'll start digging into pseudocode for PA2. So I'll see you back in about 5 minutes. All right, let's start breaking down PA2. Give me one sec. All right, so as I mentioned last time, there's different directions in which we can tackle the pieces of PA2. We can do a purely top-down approach where we begin by writing the main program, and then we move to lower and lower level functions. We can do a pure bottom-up where we begin with the lowest level functions, which for us would be my get car, and then we build up from there, or we can do a mix of those. And there's no one approach that's inherently better or worse than another. It's largely personal preference. But one thing, when I write code, I like making progress, especially in the beginning of a project. I like feeling that I'm making forward motion. And so when I'm first starting, especially a larger program, I want to do something that I'm pretty confident I know how to do, so that I get away from the empty screen syndrome. I don't have to, you know, stare at a blank VI window and wonder, what should I write? So I try to pick a piece that I'm pretty confident I know how to at least begin, and try to get some piece of code that works, that I can compile and I can run with a test program. And then I'll start adding details to it after that. And so if we look at the pieces for PA2, one thing to note is that there's a hierarchy of behavior. So we have this function called myGetCar. And this is used by another function named getWord. And getWord is going to be used by our main program, which is the index program. So our main program is basically going to get a word, add it to our tally, right? Tally it up, get a word, tally it up, and so on. And myGetCar is really going to use this getCar function that's available in C. And getCar, in fact, is going to use some low-level function called read. And read is going to use some low-level method called an interrupt, a hardware mechanism to actually do low-level I/O. And index itself is going to be called by bash. We're going to have a bash prompt, and we're going to say index enter. And bash is going to make a call to the main program inside here. So there's always this hierarchy of things calling or depending on other things. And the parts that we're developing are just, you know, this part mainly. And myGetCar will call getCar. We don't really care how getCar does its thing. So let's talk about general strategies first, and then we'll look at pseudocode. Let's say I want to develop getWord, and getWord is probably the trickiest of these functions, probably the most complex. So let's say we decide we're going to tackle that first, because I want to get the hardest one out of the way, right? Well, getWord has to use myGetCar to read a character, convert it to uppercase, ignore it if it's punctuation, and so on. But I don't have to do that. I could just have get word use get car. And if my input is something like this, hello space, cool, hello, bye, cool, hello, and a new line, right? Get car is going to work great. I'll make my input be all uppercase. I'll make sure my input doesn't have punctuations and digits and things like that. And get car is doing the same thing as what my get car would do now. So I can start working on this without developing this piece first. As long as I understand that, you know, at some point I need to write my get car so that if I have input like this, get word sees it as, you know, uppercase letters. And if I have input like this, get word will see it as not having that punctuation inside, and so on. Or maybe I don't want to tackle this yet because it is the most complex of all the functions. Maybe I want to tackle some other part, like, you know, tally. Well, I could, instead of using get word, I could just use fgets. And to test it with this input stream, I would simply feed it input where each word is on a separate line. And now fgets, you know, will come back and it will give me the next line, the next word of my input. And now it could, you know, tally up a hello, a cool, a hello, a bye, and so on and so forth. So you have options, right? And we're gonna go through an outline for each of these functions and for the main function. And you can choose which one you want to develop first if you haven't started developing any of these, or which one you want to dig for further into next, right? But we'll talk about all of these functions and we'll outline them right now. But leave open this possibility of, you know, changing the assignment temporarily to say, hey, I'm not going to do the uppercase conversion. I'm not going to do the breaking of things into words. I'm just going to use fgets and assume each word is on a separate line. And then you can work on your tally function. Or, you know, you can work on reading the keywords, and that doesn't require any of these other functions. All right, so let's start with get word. And so get word reads from standard in, and it basically breaks the input into what we consider to be words. And roughly speaking, you know, a word is a bunch of letters followed by stuff that's not letters. And if get word is calling my get car, it's never going to see lowercase letters. It's never going to see digits or punctuations. It's never going to see new lines or tabs. It's only going to see uppercase letters and spaces and eventually an end of file. And that's it. So when we're writing get word, we're going to call my get car. It's going to return either an uppercase letter, a single space, or end of file. And if we haven't written my get car yet, just use get car and only give it, you know, uppercase letters, single spaces, and end of file. So what does get word do? Well, imagine your input looks like this. So there's hello, there's a bunch of spaces, there's cool, there's a bunch of spaces, there's another word, there's a bunch of spaces, and so on. All right, so we're going to use get car or my get car. So we're going to read one character at a line. So different from the ODPs. The ODPs, we had an input string and we started marching through it. Here, we're just going to use, you know, some version of get car to get one character. So get a character. If C is a letter, add to our result. Go back and get another letter. So we'll start off with, result equals an empty string. So just like mix, start off with result bracket 0 equals \0. Oh, we didn't do that in mix, but in 416 we'll do that. So start off with an empty string, get a character. If it's a letter, add it to our result, go back and get another character. If that's also a letter, add it to result, go back, get another character. If C is a space, then we'll just return our result. If C is end of file, we have a special flag, we return null. That is 90% of get word right there. So start with an empty string, get a character. If that character is a letter, add it to your output string, get another character. If that's a letter, add it to your string, get another character, keep going. If you encounter a space, just return the string that you built up. If you encounter end of file, just return null.
Can I ask a question?
Definitely.
Can we do the while loop instead of if in this function?
So you'll definitely want to use a while loop of some sort here, because this arrow going back and doing this again means that all of this should go inside some kind of loop. And so there's a few different ways to do this. You could make an infinite loop, while one, and C equals my get car. If C is a letter, add it to your result, and then you can say continue, and continue means go back up to the top of the loop. If it's a space, return. If it's an end of file, return. Those will get you out of the loop.
Okay, thank you.
Yeah, and let's continue on that. So if we wanted to actually put this in code, we could do something like while one, C equals my get car. If C is end of file, return null. If C is a space, return your result. And I'll put a little footnote here. Otherwise, add C to result. And that's a perfectly fine infinite loop. We'll leave this loop if we hit end of file or we get a space. Otherwise, we get a character, we add it to our result, we'll get another character added to our result. That'll take care of this looping back to the beginning.
So basically what's happening here is it's iterating through letters, and then it's either hitting a space and it's saying that since there's a space, this is a full word, and it will return that word, and then there's something
Correct.
else telling it to go again. Okay, cool. Thank you.
Got it. Yeah. And to do this, absolutely perfectly, if we hit end of file while we were already building a result, we'd want to return that result. But in practice, and for any debugging I'm going to do on this, I'm going to have a full line that ends with a new line, and your my get car will change that to a space. So the last word in any tests that I do on your code is always going to be followed by a space, and that'll be followed by end of file. So So you don't have to worry about that case. But if you want to do that, yeah, and end of file could be treated as a space. But yeah, this should work. And end of file should always come right after a space, new line in particular. So we need two other things to make this the full version of get word. The first thing is when it says return result, before we do that, we need to terminate this string, just like we did in mix, just like we're doing in 416 and 417. If we're appending these letters by just storing them in next locations in the output array, we need to put that null terminator in there. So before we return, we want to copy, a quote \0 somewhere into our output string and then return it. And that ties into this business of how do we add a letter to the result? Well, this is, using this output location. And each time we want to add a letter, just copy it to, result bracket output location and then increment output location. And so we can make this code a little more precise. Start with an output location equal to 0. And to add C to the result, we just say out result bracket output location equals C, and then increment output location. And then to terminate our string, store your null terminator at the current output location and then return result. Sorry, this is result. So yeah, so there's one other detail we need to take care of, which is what if we have multiple spaces? So this code right now, it'll see the H, put that on result, E, L, L, O, those will all get added to result. When it reads this space, it'll say that's a space, it'll terminate result, and it'll return hello. But the next time we call get word and we say get a character, it's going to see a space. And it's going to say that's a space, it's going to return an empty string. And we don't really want it to do that. So in the very beginning, we're going to add one more step, which is skip over leading spaces. This takes care of where we have spaces in the beginning of our first word, or if we have multiple spaces between words. So how do we skip over spaces? So you could do something like that. Get the next character from the input. While it's a space, get the next character from the input. If that's a space, get the next character from the input. So this will keep looping until you get something that's not a space. And now, add it to your output result and then start in with this loop. Or, you could do this as an infinite loop. And we can use the break keyword to say get out of the loop. So inside this infinite loop, we'll get a character. If it's a space, we'll break out of the loop. If it's not, we'll go back up, get another character. If that's not a space, we'll go back up, get another character. If that is a space, we'll say break, which takes us out of the loop. And when we come down here, C is the first letter for our result. So now we probably want to do something like result bracket output location equals C, and then incremental output location. And then that should be pretty solid pseudocode for get word. And remember, we're given an argument, which is the car pointer where we want to store our result. So we don't have to declare a result inside this code. That's the argument that we're getting. Good so far?
Can you talk about that while loop again that you made for the spaces? So,
This one or that one?
how about the one with break? So if C is equal to a space, it just breaks the loop. Is that right?
Yeah, so break basically says jump down here. Go outside the loop, stop looping.
Okay. Does that work if there's like a double space? Or is everything else in this loop as well?
So the first space you encounter will kick you out of first space you encounter will kick you out of here. Sorry, this should be not equal. Thank you.
Oh, okay.
If it's
Yeah.
not a space, then we kick out. So yeah, that makes more sense.
Thank you.
Yeah, thanks. How do we check if getCar reads end of file? So getCar returns an int, right? And you have to declare it to return an int, not a car. And EOF is a symbol that's defined for us in standard IO. So inside here, we could do something like, you know, if C equals EOF, return null. Or down here, you know, we could say if C double equals sign EOF. Thank you. Return null. And getCar returns an int, which we'll use as a car, but it's actually an int. And if you declare it as an int, EOF is a symbol that's available to us. My getCar needs to check for end of file from getCar. And if it finds it, then it needs to return that. Because get word is using the result of my getCar. This has got to give back an EOF. But we'll do my getCar next, and I think that'll make it clearer. All right, so yeah, let's do my getCar. And this is really just wrapper around getCar. So the intended behavior is get a character. If it's a letter, convert it to uppercase and return it. If it's any kind of white space, return a single space. If it's not a letter and not white space, read another character. And if it gets end of file, return end of file. All right, so what do we do here? So call get car. Let's save the result in an int. I'm just going to call it C. And what do we do? If C equals
By the way,
EOF,
you're not showing the paper.
thanks. If C equals EOF, we'll return end of file. If C is a space, so we can use this is space function from C type. If C is a space, return a single space. So now if it's a new line, a tab, anything else, it'll just return a space. So if it's a letter, and so our function for that is alpha, then we want to return the uppercase version of that. So we can return to upper of C.
Random
Otherwise-
question.
Yeah, go ahead.
So is alpha and two upper built-in functions to a header file, or do we need to make those two? Sorry.
So no, good question. So you need to include C type. And C type.h defines all of these really useful helper functions, like is alpha, is digit, is lower, and so on. And also defines these things like two upper, two lower, and so on. And so you're allowed to include C type.h, and you're allowed to use these functions. And they do all of the nitty gritty work of looking at ASCII codes and seeing if they're between this and that, and so on and so forth.
Okay, thank you.
Yeah, you're welcome. All right, so if C is a letter, which is what is alpha tells you, then return to upper C, which takes it, and if it's lowercase, makes an uppercase value and return that. If it's not end of file, it's not a space, and it's not a letter, it's a digit, a punctuation, something weird, something we want to ignore. We want to go back to the top and get another character. So you can throw all of this inside a while one loop. And if you don't return because of one of these statements, you'll go back to the top, get another character, try again. So that's really your whole myGetCar. And keep in mind the suggestion that as you write these functions, be testing them. Don't just write this and then write myGetWord and then write tally and then try to compile and link it all together and test it out, right? Write a main program that just repeatedly calls myGetCar and prints out the result. And if you give it, some arbitrary piece of text, it should give you back just letters that are uppercase or spaces, and it should squeeze out all the other stuff. Testing that, helps you put this code to rest. It's like, okay, this code works. This is what the function does. It's doing it correctly. You can forget about this, right? Don't delete it, but you don't have to think about it anymore. You don't have to worry about it. And it also helps you really, really get a good understanding of what this function does. You can read, the description of it, and it's long and wordy and so on and so forth. But if you've written the function, and then you've written a main program to exercise it, and you've studied the results of that main program to confirm that this works, you got a really good understanding what myGetCar does. And now when you're working on getWord, and you're at a point where you want to use this function, you won't be as concerned about, wait, what does myGetCar do, right? You're going to know exactly what it does. You're going to know exactly why you want to use it and where you want to use it and how you want to use it. So this is part of this modularized development, right? Is write smaller pieces of code, but then work with them, test them, debug them, exercise them. document them, right? So I strongly recommend while you're doing this, put in lots of good commenting, right? Make sure you're really clear what's going on in each of these steps, and put your block of comments at the top, you know, with your name, the class and date and all that stuff that you need for the points, and say, you know, this is the myGetCar function. This reads in, you know, a single character, and as long as it's this or this, it'll return it. Otherwise, it'll do this and this other thing, and so on and so forth. All right, so is space takes a single character. So we read one character, and if it's a space, we'll return that. So if our input is something that contains, you know, multiple spaces, each time we call myGetCar, it'll return one more space. So myGetCar doesn't handle the multiple space issue, but that gets handled by getWord, which, for example, in the beginning skips over leading spaces. So we begin with a loop that says, hey, if I've got a space, let's call myGetCar again. So if there's 5 spaces before you get to the start of your next word, this will loop 5 times. Each time it gets another character. If it's a space, it gets another character. The last time through, it'll get the actual first character of your word, and then continue with this set of code. Right, so this, all it's doing with spaces is changing all the different types of spaces into, you know, a single space each. But if you had 10 new lines in your file, then each time you call this, you would get back 1 space for one of those new lines. But then getWord will take all of those and ignore them. Awesome. All right. So we've got myGetCar and we've got getWord. Display is just a for loop, right? Display, we're calling it, we're giving it the array of keywords, the array of how many times each keyword occurs, and the number of keywords we have. And this is just one for loop with one print statement, right? For I equals 0, I less than num keywords, I plus plus. Print out keywords bracket I and tally bracket I. And you'll be doing this, you know, in your debugging statements anyway. So this is a really straightforward function to write. And you'll want to write something like this when you're testing your read keywords function. And so we can sketch out some code when we get to that. So that's half your functions right there. Read keywords we've talked about in a little more detail before, but let's look at that. So read keywords takes 2 arguments. The first is the name of the file you want to read. So that's a car star. And the second argument is where you're going to store the keywords that you read. And that's just a fixed size array of 100 by 32 characters. So we can declare that as actually, you know, a car keywords 132. All right, so first thing you want to do is open the file. So file name is the name of the file you want to open. Open it for reading, so put the double quote R for the mode. FP is a file star. So you can go back and look at the sample code if you want to see the syntax for all of this. But, you know, open the file. And if FP is null, it means it couldn't open the file. Well, this function, if the file cannot be opened, it should return a -1. So if FP is null, just return a -1 and we're done. Otherwise, what do we do? Well, we want to read one line from the file. So we're going to use fgets. So we're going to have to read into, some kind of array. We're going to have to tell it how long that array is. We're going to have to tell it where to read from, which for us is going to be FP, because that's how we open the file. So you've got to declare string to be an array. All right, so here's a preliminary version of read keywords. Read a string from the file and then save str in the keywords array. Well, we don't know how many keywords we're going to get, but whatever the first keyword is that we read, we want to store that in keywords bracket 0. And the second word we read gets stored in keywords bracket 1, and the third in keywords bracket 2, and so on. So we're going to need a variable. We're going to want to store this in keywords bracket something. And we're going to want to copy string into that location in the keywords array. So someone asked in chat, shouldn't it be fget string 32 FP? Technically that would work. You might actually need 33. But this is just saying, I've got enough space for 100, but I've guaranteed in the assignment that you'll never have more than 32 characters in your keyword. So this will cause no harm, but it gives you a little bit of breathing room. If you make it 32 or 31 or 33, maybe that's not quite enough. Maybe it's a little more than you need. So I don't want to think, right? So I'm just making it a big array with lots of space. But technically, since our word can contain 31 characters followed by a null terminator, when we call fgets, if there's 31 characters, there's a new line at the end that's 32, and then we need one space for the null terminator. We'd actually need to get to fgets 33. fscanf is like scanf, but reading from an arbitrary file instead of just from standard in. I'm going to say, try to use fget. fscanf will work in this case, but if you wanted to read input that had spaces in it, fscanf is not what you want to use. It will break its spaces. So I'm going to say stick with fgets for reading from the keywords file. But yes, you could make it work with fgets, with fscanf. All right, so our first string gets stored at location index 0. Second string is at index 1, next one at index 2, and so on. We need a variable to go here so that we don't store all of our strings in the same location. So we're going to use another variable. All right, so we'll use something like int index, initialize it to 0. And then in here, we'll just say keywords bracket index. So we'll copy string into that, and then index equals index plus 1. All right, so here's the really, really sneaky part about copying strings. We cannot use an equal sign to copy strings. So two things to remember about strings in C. Using double equal sign to compare strings usually does not work. we have to use a function called string compare. And the second thing is copying strings using an equal sign usually does not work. We have to use a function called string copy. And so string copy takes two arguments, a destination and a source. And so string copy keywords bracket index comma string would say, take the contents of this string and copy it into this string. And yes, you can avoid all of this by putting keywords bracket index right in here and getting directly into that array element. All right, so we've got to use string copy. That's an important detail. I keep doing, keywords bracket index equals index plus one. Remember, instead of index equals index plus one, you can say index plus plus. And that means, set index equal to index plus one. And if we're careful, we can do that right in here. And say keywords bracket index plus plus. And that means first use keywords bracket index. And then when you're done, increment index. So that combines this step and this step into one. Either way is fine. There's a lot of different ways you can do this, but you'll see this a lot. And this is how I'll generally write things. But that's all it's doing. It's saying after you use keywords bracket index, do index equals index plus one. All right, so this will read, the entire input file, one line at a time, store each line into this keywords array, increment index. And when we're done, close your file. And then you're supposed to return the number of words that you read. Oh, there it is. Function returns the number of words read. So let's look at this index variable that we set up. So index equals the location where we store the next word. That's the main thing we're doing with this. Location index is always where we want to store the next word. So index starts at 0, we store the next word we read at index 0. And then we increment index to 1, and that means the next word that we read gets stored at location 1. So index is where we're going to store the next word. But there's a second way to interpret index. This is also the number of words that we've stored. So before we've done any reading from the file, index is 0. That's telling us we haven't stored any words. The first time through this loop, we'll get one string, we'll store it in here, index increments to 1. That 1 tells us we've read one word. So at the end of this whole procedure, whatever the value of index is, if index is 5, we're guaranteed we've read and stored 5 words. So if we simply return index, then our read keywords function is returning the number of things we read. All right, so this whole thing has to be a loop. Right, get a string, store it in our keywords array, increment the index. Get a string, store it in our array, increment the index. So we keep doing this, right? Loop until f gets returns null. And we've done code for that. We can say, you know, while null is not equal to f gets, and put this all in a while loop. We could put this in a while one loop, you know, a forever loop, and say if f gets equals null, then break. Otherwise, save it in here, and then it'll just go back to the top of the loop and so on. All right, and there's one important detail missing from this still, which is after we call f gets, we need to do a little bit of processing. We need to remove the new line from the end of that string, and we need to convert to uppercase. If we did while f gets equals null, that would exit if we're not at the end of the file. So f gets returns null when it hits the end of the file. So if we're looping while f gets is equal to null, the first time we call f gets, if it reads anything, we would exit our while loop. Yeah, so not equal would be exactly right. You got it. All right, so we looked before at how to get rid of the new line from the end of a string that we get from f gets. Whether from FP or standard in, it doesn't really matter. So our trick was str bracket string length of str minus 1 equals quote backslash 0. So if our string is ABC, str len is 3, string length ABC with a backslash n. Our string length is 4, string length minus 1 is 3. That's right where the new line is. If we change a null terminator and put it right here, this string becomes ABC followed by a null terminator. So that was our trick we did last week or the week before to get rid of the new lines. And then to convert a string to uppercase, iterate across the characters, and you can just say string bracket I equals to upper string bracket I. Right, and this just goes through each character of your string, and if it's a lowercase letter, this will return the uppercase version, and we just store that right back in the ith element. All right, so that's read keywords, and read keywords, you know, you can develop that without doing any of the other pieces of the program. Yeah, fgets puts a null terminator at the end of the line, so the return from fgets would actually be ABC new line null terminator. And if we want to get rid of the new line, then we need to put a null terminator right here. And so our string would actually end up being ABC null terminator. But from the perspective of a string, it's just the string containing ABC. All right, so you can write this, you can test it and debug it on its own. So all of those things make the tally function a pretty straightforward task. So tally. It takes 4 arguments. This line is probably longer than you know the rest of the program. So let me copy this over. It takes the first argument, which is a word. It takes an array that's 100 by 32 of keywords. It takes a tally, which we call count, and it takes the number of words. All right, so 4 arguments: the word we're trying to tally, the array of keywords, the array of how many times each keyword appears, and the number of keywords that we're working with. And the idea here is that, you know, keywords might be something like, you know, hello, cool, bye. And this is an array. And there's what we call a parallel array, which we're calling count. And each element in this array tells us how many times that corresponding element appears. So if hello occurred 5 times, this will be 5. If cool occurred once, this will be 1. If bye occurred 3 times, this will be 3. And if this was our whole list of keywords, then num words would be equal to 3, 1, 2, 3. So suppose we call tally with a new word like cool, and the list of keywords in our array of counts and num words is 3. How do we tally that word up? So we're gonna look from from 0 to num words minus 1. If num words is 3, our last index is 2. If num words is 3, our last index is 2. Remember, there's this off by 1 business because we start from 0. So from 0 to num words minus 1, if word equals keywords bracket I, increment count bracket I, and return. And that's really the whole program, the whole function. Just iterate over all the keywords, and for each keyword, see if it's equal to your word. And if it is, increment the corresponding count and return. So now if I call this with cool, it'll say, okay, I equals 0. Is this word cool? No. Okay, I equals 1. Is this word cool? Yes. Let's increment this count and we'll return. And then if I call it with the word, you know, fancy, is this fancy? No. Is this fancy? No. Is this fancy? No. We're done with the for loop and our function exits, and nothing got tallied. So the one tricky part in here is this. And remember, we cannot use double equal signs to compare strings. So we have to use a function called string compare. So get to know your manual pages. So here's the manual page for string copy, for copying from a source string to a destination. Here's the manual page for string compare. So string compare takes 2 strings, and it tells you if they are the same. And it tells you the return value is less than, equal to, or greater than 0 if S1 is found to be less than, to match, or be greater than S2. The only part we care about is 0. So to say if word equals keywords bracket I, we can say 0 equals string compare word, comma, keywords bracket I. And that's the comparison to see if these 2 words are exactly the same. Good. So this just leaves the main program index. And the idea of breaking our program into these functions is to make the main program really, really simple. So what's our main program do? We've got to declare some variables and so on and so forth, but basically we're going to say number of words equals read keywords. A file name, which is supposed to be keywords.txt, and an array called keywords. So we've set up, keywords to be a 100 by 32 character array. So first thing we do, call read keywords. Tell it the name of the file it should read from and tell it where it should store those keywords. And save the result in this integer numwords. If numwords is -1, print an error message and return. So if we can't open the file, if the file doesn't exist, etc., this will return a -1. This will say, hey, we couldn't process keywords.txt. Otherwise, we've got our keywords loaded into memory, and now we just make a loop. So call getWord to read a single word. And if it does not return null, if you haven't hit the end of the file, call your tally function. With the word and the array of keywords and the tally count that you've initialized to 0 and the number of words. And you can initialize your count by saying, integer count bracket 100 equals curly bracket 0. That initializes this to be all zeros. And this is your whole tally loop. Get a word, tally it, get a word, tally it, get a word, tally it. When you hit the end of the file, display results. That's the end of your main program. So it's really just a bunch of function calls to the other functions that you've written. Read in the keywords, make sure that it's succeeded, and then loop, read a word, tally it, keep doing that till there's no more words, and then display your results. So when you modularize in this way, a lot of times your main program is the simplest to write. But it's the one that kind of does the least work itself. It really just, defers all of its work to other functions. Hey, you go read some keywords. Hey, you get me a word. Hey, you tally up that word. Hey, you display the results. And the main program is just the boss at the big desk, just telling the other functions what to do and getting all the credit because it's, the main program. So there's a business model. Does the 32 character letter limit for words include the new line? So I'm not going to play with the edges on this, but just for completeness, under assumptions, each word will be no more than 31 characters, 32 if you count the null terminator, and will be comprised of only letters. So I might give you a word containing 31 letters, which means if you read it from a file, you will read 31 characters, and then you'll see a new line. And so you'll end up ingesting 32 characters. which would mean that you would need to give fgets at least 33 so that it also has space to store the null terminator. But when you take off the new line, the keyword itself, which consists of only letters, will have no more than 31 letters. And so when you store it in the keywords array, right, you'll have 31 spaces for letters and then a 32nd space for the null terminator. But I'm seriously not going to play with that. I'm not going to give you keywords with 31 letters just to test that. I did this just to make it simpler so we didn't have to dynamically allocate memory. So I won't be trying to break your code with that. All right. Hopefully that helps. That should give you some more specifics to work on if you're stuck or having trouble starting PA2. That should give you some code to begin with and some ideas on how to move forward and develop pieces. You're very welcome. All right, we've got 12 minutes left. Let's start talking about debugging. And debugging is one of the three pillars that I claim go into making a really strong programmer, right? So rapid prototyping, data structures, and debugging are three powerful keys. Debugging is not about writing perfect code. If you always write perfect code, you don't need to know how to debug code because you never make a mistake, right? But inevitably, you know, we all write code that contains bugs, unintended behaviors, things that we forgot, things that are different from what we wanted. And debugging is ultimately the process of getting rid of those bugs, but it's first the process of finding them and then understanding them. And it's really, really important as you're getting better at programming. If you write a piece of code and it doesn't work, you really want to understand why it's not working. Don't just delete it and try something different. And so this is one of my mantras that I'll repeat again and again, which is bugs are important. They will help you improve your coding skills. And so on that Canvas link, there's a link to another book I wrote mainly for 222, 223, but also a bit for this course. It's a book of haikus because I find myself saying the same things over and over and over again. And so I decided to put them into poetry. And so here's the relevant haiku for this topic. This is about bugs. It says, when you find a bug, you received a special gift. It is just for you. All right. So what does this mean? If you're writing code to do get word, right? And you run it and most of the time it works, but once in a while it breaks, right? It gives you a seg fault or it drops a character or something like that, right? That is a really, really valuable learning exercise. That is better than any ODP that I could dream up. It's better than any exercise you can find in an online tutorial, because that is an exercise specifically designed, tailored to show something that you're not quite getting right, right? And that's what you want. You don't want to do 500 homework problems if you know how to do them. You want to do that one homework problem that trips you up. Well, that's what a bug is, right? It's, I want to do X, I've written code to do X, it does Y, right? That's the thing you want to drill into. So don't ever delete your code if it has bugs. If you're racing the clock, copy it somewhere else and do whatever you can to get your code working. But at some point, go back and understand that code. And so one of the tools that will help us understand bugs is GDB. So this is the GNU debugger. If you've done Engineering 270, we use a debugger in there to step through our code. It's exactly the same idea. So GDB is a tool that will let us run our code in some cases, one instruction at a time, but look at what's happening while the code is executing. And while it's executing, we can look at the values of variables. We can type in statements to see what certain things will evaluate to. And if we really think we understand what the code's supposed to do, by stepping through it one line at a time and seeing what it's actually doing, eventually we'll see a disconnect. And that's the golden moment. That's when you know, oh, you know, I typed if x equals 0. And up here, you know, I checked x and x was equal to 5. But this statement, you know, executed for some reason. Why? Because I used a single equal sign instead of a double equal sign, right? And once you work through, you know, a long debugging session and you find a mistake, chances are you won't repeat that mistake, or you might. But if you repeat it, you'll find it quicker the next time. And after you repeat it enough times, it will, you know, you'll be alert for it as you're writing code, and you'll avoid making that mistake in the first place. So GDB is a really valuable tool. We're going to spend a lot of time this course looking at it. And in 222, we're going to be absolutely dependent on this for debugging our code. Yeah, so having a wrong branch condition in assembly language, really maddening, right? And assembly language in particular, the code all looks so much alike. And changing one letter in an instruction does something opposite from what we thought. And yeah, these 4-hour debug sessions, they are a pain while you're going through them, but you know, they're good learning lessons in the end. When you come out the other side, you've learned something fundamental. So my longest debugging session personally was 2 weeks, and it was 5 or 6 hours a day for 2 weeks solid until I figured out what the bug was. And it was a big aha moment. It was something I had never thought of before. So these are good. Yep, yeah, division issues, same thing. All right, so we've only got 5 minutes, so let me just get you started on the very basics of this. When we compile a program, we say, you know, -o main and blah blah blah. We're going to want to put an extra switch in the beginning, which is -g, and G says I want to include debugging information. And if we build an executable program where we've put a -g switch in the beginning, now we can debug this by saying GDB and the name of the executable program. And so let me just get us started on this, and we'll dig further into this on Thursday. And there's a link in Canvas to a debugging video that's pretty short. It's like 15 or 20 minutes, but it goes through everything that we're going to be going through on GDB. So here's a sample of, you know, my mix code for ODP 414. And let's say I want to test this. So I'm going to make a main program. And I'll prototype my function. And here's my main program. And I'll make an output array. And I'll call my mix function. And I'll print out the result. And I'll put in angle brackets just to be clear where it ends. So, you know, I'm doing ODP 414. And I want to mix these strings together. So I'll compile main.c and mix.c into an output file, and I'll run it, and it doesn't work. I should have gotten A1, B2, C3, instead I got AB2. So first thing I'm going to do is I'm going to compile it with a -g switch. And then to debug it, I'm going to say GDB and the name of my main program. And it's going to bring me into this debugging environment. And so it tells me, a bunch of information up here, licensing information and so on. This is what I want on the bottom, reading symbols from main done. That tells me that I use the -G switch and it's ready to go. And I'm going to begin this by saying start. So that's how we always start our debugging sessions. And now if I say list, I can see my source code. So there's my main program. And I can start executing my program with one of two commands. I can say next, which will execute the next statement, or I can say step, which will also execute the next statement. The difference between these is this is what we call a step over. This is what we call a step into. When we step over, we're saying if the next statement is a function call, run that whole function and then come back. If it's not a function call, then go ahead and if it's a function call and we step into that function and come back. So I got a statement up here saying temporary breakpoint main.c line 5, which is our curly bracket. So let me say step. And it tells me it's about to execute this function mix. And if I say step again, it actually goes inside this function. And I can see the arguments. The first argument was called S1, and that's got the string ABC. The second argument is S2, and that's got the string 1, 2, 3. The third argument is out, and that's an empty string. And I can say list, and here's, where I am in my source code. I'm about to execute line 7, which says integer outlook equals 0. So, all of this stuff is part of my program, but when I called my function, it's about to execute this statement. And so I can say, step or next, and it will execute that statement. Now it's about to do this for loop. So it always shows me the thing that's about to be executed. And while I'm in here, I can say something like, let's print the value of outlook. Well, that's a 0. Let's print the value of S1. Well, it's a string ABC, and so on. So I can start stepping through my code, and this should copy my first character into the first character in my output string. So I can print out, and hey, it got the letter A, and I can step, and this should copy the first character of my second string into out, and I can print out, and hey, there's an A1. So far, so good. And I can step again, and this should copy the second character of my first string into out. And if I print out, instead of being A1B, it's AB. So something went wrong. All right, so we got to end it here, but if we go through this, we'll do this on Thursday, right? And we look at what the code is supposed to do, because we've got comments in our code, right? And we see that instead of getting A1B, we got AB. We're going to use that to drill down into this and figure out where the bug is. So we'll play with that on Thursday and get a better idea of this. And like I say, you can take a look at that video posted on Canvas on using GDB. And also, I don't think I have a link to that haiku book, so I will put that in Canvas. So step over means the same thing as step into, unless you have a function call. If it's a function call that's about to be executed, step over executes the whole function and then comes back. Whereas step into starts executing the function and comes back in the beginning of that. All right, so we're out of time here. I will leave it at that. I will go ahead and upload this to YouTube. If you came into class late, go back and listen to the beginning of this recording. I put in all the disclaimers and caveats and ways you can let me know if you're uncomfortable with having the lecture recorded, how we'll deal with that. And it's easy to deal with. So go ahead and catch that. Otherwise, have a good rest of the day, and I will see everybody next time. All right, thank you.
Thank you.
Bye.
Bye.